Max Planck was born on the 23rd of April, 1858, in Kiel, a port city in northern Germany. He was the son of Johann Julius Wilhelm Planck, a law professor at the University of Kiel, and Emma Patzig, whose family was rooted in the academic and cultural circles of Germany. His parents were both deeply involved in the intellectual life of the period, which would shape Planck's formative years. The Planck family was highly regarded for its academic and professional achievements, which played an important role in Max's early development. Max was raised in an environment that valued knowledge and intellectual pursuits, and it was clear from a young age that he was a child prodigy with a keen interest in the sciences. Growing up in a family of scholars, Max Planck was exposed to academic discussions and intellectual debates from an early age. His father was an accomplished professor of law, and his mother came from a family of well-educated individuals. As a young boy, Max Planck was not initially drawn to physics, but rather to music. He was particularly fascinated by the piano, and it was not until later that he realized his true calling was in the realm of theoretical physics. His early exposure to the arts would have a lasting impact on his approach to scientific thinking. He often mentioned that he found beauty in science, just as one might find it in music or other forms of art. Planck's interest in physics began to take shape when he enrolled at the University of Munich in 1874. Initially, he had planned to study engineering, but after a year, he switched to physics. This shift marked the beginning of his lifelong commitment to understanding the fundamental laws of nature. He was captivated by the works of leading scientists such as Hermann von Helmholtz and Gustav Kirchhoff, whose ideas on thermodynamics and the nature of energy would influence his future work. At the university, Planck was under the tutelage of prominent physicists who exposed him to the latest advancements in the field, including the pioneering work of Ludwig Boltzmann on statistical mechanics and the thermodynamic theory of heat. During his time at Munich, Planck became increasingly absorbed in the study of energy and heat, and this interest would eventually lead him to his most groundbreaking discovery. After completing his undergraduate studies, Planck went on to earn his doctorate in 1879 from the University of Munich. His dissertation, titled On the Second Law of Thermodynamics, demonstrated his growing fascination with the fundamental principles that governed the behavior of energy and matter. Planck's early work was largely focused on thermodynamics and the problem of energy distribution, a topic that was of great interest to physicists of the time. The search for a deeper understanding of heat radiation, particularly the phenomenon of black body radiation, would soon become the focus of Planck's most significant work. Despite his early success, Planck struggled with the constraints of classical physics, which was based largely on the laws of thermodynamics and Newtonian mechanics. These theories were immensely successful in explaining the macroscopic world, but they encountered difficulties when applied to microscopic phenomena. This discrepancy was particularly evident in the study of black body radiation, which refers to the radiation emitted by an idealized object that absorbs all incident light. Classical physics predicted that black-body radiation would increase without bound as the wavelength of light decreased, an issue known as the ultraviolet catastrophe. This problem, along with others like it, led to a growing sense among physicists that a new approach was necessary. In 1894, Planck was appointed as a professor at the University of Berlin, where he would continue his work on thermodynamics and radiation. At this time, the field of physics was undergoing a period of intense transformation, with many scientists beginning to question the validity of classical theories. The works of scientists such as Wilhelm Röntgen, who discovered X-rays in 1895, and the early theories of quantum mechanics, proposed by Max Einstein and others, were beginning to open up new possibilities for understanding the fundamental nature of matter and energy. Planck, however, remained deeply rooted in the tradition of classical physics and did not immediately embrace these new ideas. The turning point for Planck came in 1900 when he turned his attention to the problem of black body radiation. Planck recognized that existing theories could not explain the observed behavior of black body radiation, and he set out to find a solution. It was through his work on the spectral distribution of radiation that Planck formulated the idea that energy could not be emitted or absorbed in a continuous manner, as was previously thought. Instead, he proposed that energy was quantized and that it could only be emitted or absorbed in discrete amounts, or quanta. This concept, which became known as Planck's quantum hypothesis, was a radical departure from classical ideas and marked the birth of quantum theory. Planck's quantum hypothesis was based on the idea that energy could only be transferred in specific quantities proportional to the frequency of radiation. The equation that Planck derived to describe this relationship, E equals hNIU, where E is the energy, h is Planck's constant, and NIU is the frequency, was a monumental breakthrough. Planck's constant, denoted by the symbol h, became a fundamental constant in physics and is still used today in quantum mechanics. The idea of quantized energy provided a solution to the problem of black body radiation and laid the groundwork for the development of quantum theory. However, Planck himself did not fully grasp the revolutionary implications of his discovery. He initially saw his quantum hypothesis as a mathematical tool rather than a fundamental shift in our understanding of the universe. Despite the groundbreaking nature of his work, Planck was hesitant to fully embrace the radical new theory that he had discovered. In his mind, it was merely a method for solving a specific problem in radiation theory. The reluctance to accept the full implications of his work is a recurring theme in Planck's life. He was deeply conservative in his scientific thinking, and he struggled to reconcile the implications of his discoveries with the classical worldview that had shaped his career. Planck was not the only physicist at the time to struggle with the idea of quantum mechanics. Many of his contemporaries, including Albert Einstein and Niels Bohr, would later come to accept and expand upon Planck's ideas, but Planck himself remained somewhat reserved in his acceptance of the revolutionary theory that he had helped to create. Even though Planck's work laid the foundation for quantum mechanics, he remained cautious about its broader implications and was reluctant to fully embrace the probabilistic nature of the quantum world. Planck's quantum theory, however, would eventually lead to the development of a new framework for understanding the microscopic world. Over the next few decades, his ideas were expanded upon by other physicists, including Albert Einstein, who used Planck's quantization of energy to explain the photoelectric effect, and Niels Bohr, who applied quantum concepts to explain atomic structure. The full implications of Planck's work would not be realized until after World War I, when quantum mechanics emerged as a fully developed field. Nonetheless, Planck's contributions to physics were instrumental in the development of quantum theory, and his work continues to shape the field of physics to this day. Throughout his career, Planck was highly regarded by his peers for his intellectual rigor and dedication to his work. He received numerous awards and honors for his contributions to science, including the Nobel Prize in Physics in 1918 for his work on radiation theory. Despite his personal struggles with the implications of his discoveries, Planck remained a respected figure in the scientific community. He was appointed to various prestigious positions, including the presidency of the German Physical Society, and his work inspired countless other physicists to continue exploring the mysteries of the quantum world. Max Planck's early life and academic journey reflect his deep commitment to understanding the fundamental laws of nature. His groundbreaking work on black body radiation and the introduction of the concept of energy quanta marked a turning point in the history of physics. Though Planck himself did not immediately embrace the full revolutionary implications of his work, his contributions paved the way for the development of quantum mechanics. Today, Planck is remembered as one of the most important figures in the history of physics, and his legacy continues to influence the field of theoretical physics. Max Planck's discovery of the quantum nature of energy in 1900 marked the beginning of a profound transformation in the field of physics. However, while his breakthrough was revolutionary, Planck himself remained reluctant to fully embrace the radical implications of his work. The initial response to Planck's theory was met with skepticism by many of his contemporaries, and even Planck himself hesitated to acknowledge the scale of the paradigm shift he had initiated. To fully understand Planck's reluctance to embrace his own discovery, it is important to explore his intellectual journey, the scientific environment of the time, and his personal struggles with the philosophical implications of quantum mechanics. As Planck's work continued to resonate within the scientific community, his theory faced challenges not only in terms of its acceptance, but also in its conceptual clarity. Classical physics, which had been dominant for centuries, operated under deterministic principles. Classical mechanics, thermodynamics, and electromagnetism all adhered to the belief that nature followed predictable and continuous laws. The idea that energy could be quantized, as Planck proposed, seemed to contradict everything physicists had believed about the universe. Energy was thought to be a continuous quantity, and the suggestion that it could only exist in discrete packets was, at the time, a difficult concept to accept. This transition from classical physics to quantum mechanics created a philosophical divide that many physicists, including Planck, struggled to bridge. Planck himself remained unconvinced of the deeper implications of his work. His quantum theory was intended as a temporary solution to the specific problem of black body radiation, not as a new framework for understanding all of nature. Planck's initial reluctance to accept the full scope of his discovery stemmed from a fundamental attachment to the deterministic laws of classical physics. For him, quantum mechanics was merely a mathematical tool, not a complete overhaul of the physical laws that had governed scientific thought for centuries. The underlying tension between classical physics and quantum mechanics became even more apparent as Planck's work gained traction within the scientific community. Planck's quantum hypothesis became foundational to the work of other physicists, particularly Albert Einstein, who applied Planck's ideas to explain the photoelectric effect in 1905. Einstein's work demonstrated the particle-like nature of light, further cementing the idea of quantized energy and challenging the established wave theory of light. Einstein's bold acceptance of the quantum hypothesis marked the beginning of a radical shift in physics, but it also placed him in conflict with some of the most respected figures in the field, including Planck. For Planck, the acceptance of quantum theory by Einstein was both a validation of his work and a source of unease. While Planck recognized the importance of Einstein's contributions, he was not fully ready to accept the philosophical implications of a world governed by uncertainty and probability. In particular, the concept of wave-particle duality, which emerged from Einstein's work, posed a significant challenge to Planck's classical mindset. The idea that particles, such as light, could exhibit both wave-like and particle-like behavior seemed to blur the line between the predictable and the uncertain, and this uncertainty was something that Planck found deeply unsettling. As quantum theory began to take hold, Planck's reservations about the probabilistic nature of the quantum world became more pronounced. He believed that quantum theory, while effective at explaining phenomena like black-body radiation, could not fully replace the classical understanding of physics. Planck's reluctance to embrace the full implications of quantum mechanics was rooted in his belief in a deterministic universe. Classical mechanics, with its clear laws and predictable outcomes, had been immensely successful in describing the macroscopic world, and Planck was hesitant to accept that nature might operate in a fundamentally different way at the microscopic level. This reluctance was particularly evident in Planck's interactions with other physicists, such as Niels Bohr, who advocated for a more radical interpretation of quantum mechanics. Planck's discomfort with the probabilistic nature of quantum mechanics was also reflected in his personal life. In 1912, Planck's life was tragically marked by the loss of his wife, who died following a lengthy illness. In the years that followed, he also experienced the devastation of the First World War, during which he lost several family members and close friends. These personal tragedies may have deepened his attachment to the certainty and order of classical physics. The tumultuous period of war and personal loss may have contributed to Planck's desire for a stable, predictable understanding of the universe, one that was not governed by the uncertainty and indeterminacy that quantum mechanics suggested. Despite his reservations, Planck's contributions to the development of quantum theory were profound and irrefutable. His introduction of the Planck constant, which remains a cornerstone of quantum mechanics, laid the foundation for the further development of the theory. In 1918, Planck was awarded the Nobel Prize in Physics for his work on black-body radiation, cementing his place as one of the most important figures in the history of physics. However, the same year that he received the Nobel Prize, Planck's struggle with quantum mechanics continued. He was still reluctant to accept the full implications of the theory he had helped to create, particularly the idea that the universe might operate on probabilistic principles rather than deterministic ones. Despite his discomfort with the probabilistic nature of quantum theory, Planck's work continued to influence the development of modern physics. His theory of black-body radiation paved the way for the work of other physicists, such as Niels Bohr, who developed the first model of the atom based on quantum principles. Bohr's model of the atom, which proposed that electrons could only occupy discrete energy levels, was a direct extension of Planck's quantum hypothesis. The development of quantum mechanics also had profound implications for other fields, including chemistry, materials, science, and electronics, where the principles of quantum theory are now applied daily. As quantum mechanics developed throughout the 20th century, Planck's role as the reluctant revolutionary became more apparent. Though he had initially hesitated to embrace the full implications of his work, Planck's contributions were indispensable in shaping the future of physics. His development of quantum theory, though born out of necessity to solve a specific problem, became one of the most significant scientific achievements of the 20th century. Planck's reluctance to accept the probabilistic nature of quantum mechanics was shared by many of his contemporaries, but it was this very uncertainty that would come to define the quantum world. In his later years, Planck began to soften his stance on the implications of quantum mechanics. By the 1922, as the work of physicists like Bohr and Heisenberg advanced the field, Planck came to accept that the probabilistic nature of quantum mechanics was not a flaw in the theory, but an inherent feature of the quantum world. Though Planck had spent much of his career as a skeptic of the full implications of quantum theory, he ultimately recognized that the uncertainty and indeterminacy that characterized the quantum realm were integral to understanding the behavior of particles at the smallest scales. Max Planck's journey from the reluctant revolutionary to the eventual embrace of quantum mechanics is a testament to the complexities of scientific progress. His contributions to the field of physics, particularly his work on black-body radiation and the development of the Planck constant, laid the groundwork for the quantum revolution that would follow. Planck's reluctance to fully accept the implications of his work highlights the personal and intellectual struggles that accompany groundbreaking scientific discoveries. It is a reminder that even the most profound discoveries are often met with resistance and skepticism, and that true scientific revolutions require time, perseverance, and an openness to change. Max Planck's legacy as the reluctant revolutionary of physics remains a cornerstone of modern science, and his work continues to inspire new generations of physicists to explore the mysteries of the quantum world. Max Planck's contribution to the development of quantum mechanics is often regarded as one of the most pivotal moments in the history of science. His discovery of the quantum nature of energy, while initially conceived as a solution to the blackbody radiation problem, eventually laid the foundation for what we now understand as quantum theory. However, Planck's journey towards this discovery was far from straightforward. He was deeply entrenched in the traditions of classical physics, and his initial approach was to solve the blackbody radiation problem within the framework of classical laws. It was only after he encountered the limitations of these traditional models that he was pushed toward a new and revolutionary path. The problem of blackbody radiation had been a subject of intense debate among physicists for years. Classical physics, specifically the Rayleigh-Jeans law, predicted that the energy radiated by a blackbody would continue to increase indefinitely as the wavelength of the radiation decreased. This led to what was called the ultraviolet catastrophe, where the law gave nonsensical results for high-frequency radiation. This posed a critical challenge to classical physics, and by the late 19th century, physicists were scrambling to find a solution. It was in this context that Planck stepped in, and his approach would not only solve the blackbody radiation problem, but also change the course of physics forever. Planck's initial insight came when he tried to model the distribution of energy in a cavity containing electromagnetic radiation. He sought to explain the radiation emitted by a black body, an idealized object that absorbs all incoming light and re-emits it according to its temperature. Classical physics had failed to explain this radiation, particularly at shorter wavelengths where the energy appeared to diverge. Planck approached this problem by introducing a revolutionary assumption. He proposed that energy was not emitted or absorbed in a continuous manner, as was traditionally thought. Instead, he suggested that energy could only be emitted in discrete packets, or quanta. This was a radical departure from the prevailing views of classical mechanics and thermodynamics, which treated energy as a continuous quantity. Planck's hypothesis was that the energy of these quanta was directly proportional to the frequency of radiation, and he formulated this relationship in the equation E equals hNIU, where E is the energy, h is a constant now known as Planck's constant, and NIU is the frequency of the radiation. This idea, which became known as Planck's quantum hypothesis, was the first step in the development of quantum theory. Planck's constant, denoted by the symbol h, would become one of the most important constants in physics, a fundamental quantity that defines the scale of quantum effects. The introduction of the quantum hypothesis was a bold move, but Planck was not yet ready to fully embrace the broader implications of his discovery. His initial aim was not to revolutionize physics, but to find a way to explain the observed distribution of blackbody radiation. The quantization of energy was simply a mathematical trick to solve a specific problem, not a fundamental change in the understanding of physical laws. Even though his work solved the blackbody radiation problem, Planck's reluctance to fully accept the quantum nature of energy meant that he did not immediately recognize the significance of his own work. For him, the quantization of energy was a useful mathematical tool rather than a profound insight into the nature of the universe. Despite Planck's own hesitations, the impact of his discovery was immense. His work opened the door for other physicists, particularly Albert Einstein, to explore the implications of quantized energy. Einstein, in 1905, applied Planck's quantum hypothesis to explain the photoelectric effect, where light striking a metal surface could cause the emission of electrons. Einstein's interpretation of the photoelectric effect demonstrated that light itself must also be quantized into discrete packets of energy, which he called photons. This was a direct application of Planck's work, and Einstein's findings would later earn him the Nobel Prize in Physics. The idea that light could behave as both a wave and a particle known as wave-particle duality, would become one of the central tenets of quantum mechanics. While Planck had laid the groundwork for quantum theory, he remained uncomfortable with its philosophical implications. Quantum mechanics suggested that the universe might not be deterministic, but rather governed by probabilities. Classical physics had always assumed that the laws of nature were deterministic, meaning that the future could be predicted with certainty if the current state of a system was known. The idea that quantum mechanics introduced a level of indeterminacy where only probabilities could be predicted was deeply unsettling for Planck. He had spent much of his career immersed in the deterministic worldview of classical physics, and the probabilistic nature of quantum theory was something he found difficult to reconcile. In the early 20th century, the scientific community was divided on how to interpret the new quantum theory. Planck was not alone in his discomfort with the probabilistic interpretation of quantum mechanics. Other leading physicists, including Albert Einstein and Niels Bohr, were also grappling with the implications of quantum mechanics. Einstein, for instance, famously rejected the idea that the universe was fundamentally probabilistic. He famously said, "God does not play dice with the universe," expressing his belief that there must be a deeper, hidden order behind the randomness observed in quantum systems. Despite his personal reservations, Planck's contributions to quantum theory were foundational. His introduction of the idea that energy is quantized was the first step in a series of discoveries that would eventually lead to the development of the full quantum theory. As the 20th century progressed, quantum mechanics became increasingly accepted by the scientific community, and its strange, counterintuitive principles were applied to a wide range of phenomena, from the behavior of atoms to the properties of solid materials. Planck's work on black-body radiation was the key that unlocked the door to the quantum world, and his constant, h, became one of the most important and universally recognized constants in all of physics. Max Planck's work was not just revolutionary in its implications for physics, it also marked the end of an era in scientific thought. The shift from classical physics to quantum mechanics represented a dramatic departure from the worldview that had dominated scientific thinking since the time of Isaac Newton. The deterministic laws of classical mechanics, which had been so successful in explaining the macroscopic world, could no longer account for the phenomena observed at the microscopic level. Quantum mechanics, with its probabilistic nature and focus on discrete energy levels, was a radical departure from classical thinking, and it fundamentally changed our understanding of the universe. The journey of Max Planck from classical physics to quantum theory was a slow and cautious one, marked by his reluctance to accept the full implications of his discovery. His quantum hypothesis, which began as a mathematical tool to explain black-body radiation, ultimately led to a revolution in physics. Planck's reluctance to embrace the full implications of his work reflects the common hesitation that many scientists feel when faced with new and radically different ideas. Even though Planck was not the first to fully embrace the probabilistic nature of quantum mechanics, his work laid the foundation for the development of quantum theory. His quantum hypothesis was the key that unlocked the door to the strange and counterintuitive world of quantum mechanics, and his contributions to science remain some of the most important in history. Despite his hesitation to embrace the full scope of his work, Planck's impact on the field of physics cannot be overstated. His contributions to the development of quantum theory were instrumental in shaping the future of science, and his work continues to influence the study of quantum mechanics and modern physics. Planck's legacy as the reluctant revolutionary highlights the complexities and challenges of scientific discovery, and his work serves as a reminder that even the most groundbreaking ideas often require time, perseverance, and a willingness to confront the unknown. Through his work, Max Planck helped to usher in a new era of scientific understanding, and his contributions to the field of physics continue to resonate today. ChatGPT said, Max Planck's early contributions to the development of quantum mechanics are often regarded as the catalyst for one of the most transformative shifts in the history of physics. While his work on black-body radiation in 1900 is recognized as the inception of quantum theory, his personal reluctance to fully accept the radical implications of this discovery reveals the complexities of scientific revolution. Planck's journey was not just a scientific breakthrough, but a personal and intellectual evolution that spanned decades, characterized by caution, a resistance to change, and an attachment to classical physics. His intellectual struggle in embracing the quantum nature of the universe speaks volumes about the tension between established beliefs and the disruptive force of groundbreaking new ideas. In order to understand why Planck was reluctant to accept the full ramifications of his work, it is essential to examine his intellectual background, scientific environment, and the prevailing ideas that governed physics during his early career. At the turn of the 20th century, the scientific community was entrenched in classical mechanics, a framework that had successfully explained the macroscopic world for centuries. Newtonian physics, based on deterministic laws, dominated the landscape of scientific thought. Classical thermodynamics, electromagnetism, and statistical mechanics operated under the assumption that energy was a continuous quantity, an idea that was central to the understanding of physical phenomena. It was within this classical framework that Max Planck was trained and began his academic journey. Planck was deeply rooted in the traditions of 19th-century physics and, like many of his contemporaries, believed that the laws governing nature were deterministic and continuous. His early studies focused on thermodynamics, specifically the second law, which describes how energy flows in physical systems. It was in his early work on heat and energy distribution that Planck encountered the first real challenge to the classical view of physics. The problem of black-body radiation, a type of radiation emitted by an idealized object that absorbs all incoming light, was a long-standing issue in physics. Classical physics, based on the Rayleigh-Jeans law, predicted that the energy radiated by black bodies would increase without bound as the wavelength of the radiation became shorter. This led to the ultraviolet catastrophe, an embarrassing result for classical physics that contradicted experimental observations. Faced with this paradox, Planck took on the challenge of resolving the issue of black-body radiation. He approached the problem with the mindset of a classical physicist, attempting to derive a solution within the established framework. He made several important assumptions about the nature of radiation and energy, and after a period of intense thought and experimentation, Planck introduced a concept that would change the course of physics forever. Energy is not emitted or absorbed in a continuous manner, but in discrete packets. These packets, or quanta, were directly proportional to the frequency of radiation. The equation that Planck derived, E equals hNIU, where E represents energy, h is Planck's constant, and NIU is the frequency of radiation, became one of the most significant equations in physics. Although Planck's quantum hypothesis solved the problem of black-body radiation and provided a much-needed resolution to the ultraviolet catastrophe, it was not initially recognized as the revolutionary insight that it was. Planck himself was cautious about the implications of his discovery. At first, he viewed the idea of quantized energy as a mathematical tool, an artificial construct to solve a specific problem in radiation theory. In his mind, it was a temporary solution, not a fundamental reworking of the laws of nature. Planck was hesitant to abandon the classical worldview, which had been so successful in explaining macroscopic phenomena, and was deeply skeptical of the probabilistic and discontinuous nature of quantum theory. He believed that the universe must be governed by predictable, deterministic laws, and that the introduction of quanta was merely a mathematical necessity rather than a fundamental truth about the nature of reality. This reluctance to fully embrace the quantum nature of the universe was not unique to Planck. At the time, many of Planck's contemporaries, including Albert Einstein and Niels Bohr, were also grappling with the implications of quantum mechanics. Einstein's work on the photoelectric effect in 1905, which used Planck's quantum hypothesis to explain the emission of electrons from metal surfaces, further confirmed the validity of quantized energy. However, Einstein himself had reservations about the probabilistic nature of quantum mechanics. He famously said, "God does not play dice with the universe," expressing his discomfort with the randomness inherent in quantum theory. Similarly, Bohr's work on atomic structure and his development of the Bohr model of the atom was rooted in quantum principles, but Bohr himself struggled to accept the full philosophical implications of quantum mechanics. Planck, meanwhile, continued to work within the classical framework, even as quantum theory gained traction within the scientific community. He was involved in debates with other physicists about the interpretation of quantum theory, and he was reluctant to accept the philosophical and conceptual shifts that were taking place. His hesitancy was rooted in his deep commitment to the deterministic, orderly universe described by classical physics. The probabilistic nature of quantum mechanics, which suggested that events at the microscopic level could not be predicted with certainty, was a deeply unsettling concept for Planck. He felt that accepting such a view would undermine the very foundations of scientific inquiry and the belief that the universe operates according to fundamental laws. In spite of his reluctance, Planck's ideas had a profound impact on the future of physics. His work laid the groundwork for the development of quantum theory, and his constant, h, became a fundamental constant in physics. As quantum mechanics developed in the 1920 seconds and 1930 seconds, it became clear that Planck's quantum hypothesis was not just a mathematical tool, but a fundamental feature of the universe. His ideas were expanded upon by physicists such as Werner Heisenberg, who developed the uncertainty principle, and Niels Bohr, who advanced the theory of the atom. Quantum mechanics became the framework for understanding the behavior of particles at the smallest scales, and it provided explanations for phenomena that classical physics could not account for. Despite his own struggles with quantum mechanics, Planck eventually came to accept its principles. In his later years, he acknowledged that the universe might not be as deterministic as he had once believed. He recognized that quantum mechanics provided a more accurate description of the physical world, even though it was fundamentally different from the classical worldview that had shaped his career. Planck's acceptance of the probabilistic nature of quantum theory represented a profound shift in his own thinking, and it marked the final stage in his intellectual evolution. In a sense, Planck's journey from reluctant revolutionary to accepted leader in the field of quantum mechanics mirrors the larger journey of science itself. As physicists slowly came to terms with the radical implications of the quantum world, Max Planck's story is a testament to the complexities of scientific progress. His contributions to quantum theory, though initially met with hesitation and reluctance, fundamentally altered our understanding of the universe. His pioneering work on black-body radiation, along with his introduction of the concept of quantized energy, laid the foundation for the quantum revolution that followed. Planck's intellectual journey, characterized by caution, skepticism, and a deep attachment to classical physics, illustrates the personal struggles that often accompany scientific breakthroughs. His work continues to shape the field of physics today, and his legacy as one of the founding figures of quantum mechanics remains firmly established in the annals of scientific history. Max Planck's contributions to the development of quantum theory, especially his groundbreaking work on black-body radiation, marked the beginning of an era in physics that completely transformed how scientists understand the fundamental structure of reality. Planck's contributions not only solved a key issue in theoretical physics, but also ignited a revolution that would pave the way for quantum mechanics. However, his journey was not without struggle and intellectual conflict. His early work was deeply rooted in the classical understanding of physics, and he had a profound attachment to the deterministic worldview that had long dominated scientific thought. It was only through his work on black body radiation that Planck was forced to confront the limitations of classical physics and make a breakthrough that would forever change the trajectory of science. The early history of Max Planck's career is crucial to understanding his intellectual development. Born in 1858 inches, Kiel, Germany, into a family steeped in academic tradition, Planck was encouraged from a young age to pursue a life of learning. His father, Johann Planck, was a law professor, and his mother came from a family of intellectuals. Max initially pursued a path in music before ultimately finding his passion in physics. By the time he entered the University of Munich in 1874, he had already developed a keen interest in the emerging field of thermodynamics. The study of energy, heat, and the laws that govern these fundamental concepts became the focus of his academic career. Planck's early studies focused on the works of classical physicists such as Gustav Kirchhoff and Hermann von Helmholtz, whose ideas on heat and extant energy distribution helped shape his understanding of the subject. In the late 19th century, classical physics was grounded in the notion of energy as a continuous quantity which could be exchanged freely between different forms: thermal, mechanical, electromagnetic, and others. This view was well supported by Newtonian mechanics and thermodynamics, which had successfully explained the behavior of macroscopic systems. However, as physics progressed, certain problems arose, particularly in the area of blackbody radiation. Blackbody radiation refers to the radiation emitted by an idealized object, called a black body, that absorbs all incident radiation and emits radiation at all wavelengths. Classical physics struggled to explain the distribution of this radiation, especially at shorter wavelengths, where the Rayleigh-Jeans law predicted that the energy radiated would increase without bound. This discrepancy, known as the ultraviolet catastrophe, was a significant challenge for the scientific community. At the time, scientists believed that classical laws of radiation should apply to black bodies, but experimental data contradicted this expectation. This paradox became one of the defining problems that physicists of the time sought to resolve. In response to this challenge, Planck began to investigate the problem of blackbody radiation in the late 19th century. His approach was to combine thermodynamic principles with the emerging theory of electromagnetism, which had been developed by James Clerk Maxwell. However, rather than continuing along classical lines, Planck found himself confronted with the limitations of the existing theories. The more he worked on the problem, the more apparent it became that a new approach was needed. The breakthrough came when Planck realized that the classical laws of thermodynamics could not explain the observed phenomena. It was here that Planck introduced the idea that energy is not emitted or absorbed in a continuous manner, as classical physics suggested, but rather in discrete packets, which he called quanta. This revolutionary idea, which Planck first proposed in 1900, became the cornerstone of quantum theory. According to Planck, the energy of a system could only change in specific quantized steps, and the amount of energy transferred in each step was proportional to the frequency of the radiation. This idea led to the equation E equals hNIU, where E is the energy, h is Planck's constant, and NIU is the frequency of the radiation. This equation not only resolved the problem of blackbody radiation, but also provided a new framework for understanding the interaction of light and matter. Planck's quantum hypothesis was a radical departure from classical physics, but it was a solution that worked within the existing experimental data. it also opened the door for further developments in theoretical physics. However, Planck himself did not fully appreciate the magnitude of the shift his discovery represented. Initially, he viewed the concept of quantized energy as a mere mathematical tool to solve a specific problem. For him, the quantum hypothesis was not a fundamental rethinking of the laws of nature, but a pragmatic fix to a specific theoretical issue. He was deeply entrenched in the classical worldview, and his hesitance to embrace the broader implications of his work highlights a common theme among scientists who first make groundbreaking discoveries but are reluctant to accept the profound consequences of those discoveries. This reluctance to fully embrace the implications of quantum theory was not unique to Planck. In fact, many of his contemporaries, including Albert Einstein, were initially uncomfortable with the philosophical and conceptual changes that quantum mechanics introduced. Einstein, in particular, was not fully ready to accept the idea that the universe was governed by probability and uncertainty, concepts that were central to the quantum worldview. He famously stated, "God does not play dice with the universe," reflecting his belief that the laws of nature should be deterministic and that quantum mechanics was an incomplete theory. Despite this, Einstein's work on the photoelectric effect in 1905, which relied on Planck's quantum hypothesis, solidified the experimental foundation for quantum theory. As Planck's ideas gained traction, they set the stage for the development of quantum mechanics, but Planck himself remained hesitant to accept its full implications. He continued to view his work as a solution to a specific problem rather than as the foundation of an entirely new field of physics. This reluctance was further complicated by the growing tension between classical and quantum physics. Classical physics, with its well-defined laws and predictable outcomes, had been immensely successful in explaining macroscopic phenomena. However, quantum theory introduced a level of uncertainty and probabilistic behavior that was foreign to the deterministic framework of classical physics. Planck's discomfort with this uncertainty made him hesitant to fully embrace the implications of his own discovery. Despite his personal reservations, the impact of Planck's work on the development of quantum theory was undeniable. His quantum hypothesis became the foundation for later developments in quantum mechanics, including the work of Niels Bohr, Werner Heisenberg, and Erwin Schrödinger. These physicists built upon Planck's ideas to develop a comprehensive framework for understanding the behavior of particles at the atomic and subatomic level. Quantum mechanics soon became the dominant theory in physics, providing explanations for phenomena that classical physics could not account for, such as the behavior of electrons in atoms and the nature of light itself. Planck's legacy as the father of quantum theory is secured, even though he struggled with the broader philosophical implications of his work. His contributions to the development of quantum mechanics were foundational, and his work laid the groundwork for a revolution in physics that continues to shape our understanding of the universe today. While Planck may not have fully embraced the quantum worldview during his lifetime, his discovery of quantized energy remains one of the most important milestones in the history of science. The journey from classical physics to quantum mechanics was a difficult and often uncomfortable one, but it ultimately provided a deeper understanding of the nature of reality. In the years following Planck's initial discovery, quantum mechanics continued to evolve and expand, with physicists refining and expanding upon Planck's original ideas. However, the underlying principles that Planck introduced, the idea that energy is quantized and that the behavior of particles is governed by probabilistic laws, remained at the heart of quantum theory. Planck's equation, E equals hNIU, and his introduction of the Planck constant, h, became central to the development of modern physics. Today, the Planck constant is one of the most important and universally recognized constants in all of science, and it remains a key part of our understanding of the quantum world. Max Planck's contributions to quantum theory were monumental, but his personal journey reflects the complex nature of scientific discovery. His reluctance to fully accept the revolutionary implications of his work speaks to the intellectual struggles that many scientists face when confronted with ideas that challenge the established worldview. Planck's intellectual journey serves as a reminder that even the most groundbreaking discoveries often require time, perseverance, and a willingness to confront the unknown. Though he was reluctant to embrace the full scope of his work, Planck's contributions continue to shape our understanding of the universe, and his legacy as a pioneering figure in the development of quantum mechanics remains firmly established in the history of science. Max Planck's influence on the field of physics, particularly in the birth of quantum theory, is profound, and his journey into the heart of the quantum revolution tells the story of a man who unintentionally became the father of a scientific revolution. His work, starting with the black-body radiation problem in the late 19th century, not only solved a critical problem of the time but also laid the groundwork for the entire field of quantum mechanics. However, Planck's relationship with his own discovery was complex and marked by reluctance and intellectual struggles, reflecting the difficulty of abandoning a classical understanding of the universe. His unease with the philosophical and conceptual implications of his quantum hypothesis is a testament to the difficulty many scientists face when confronted with paradigm-shifting ideas. Before diving into Planck's contributions to the quantum revolution, it's important to understand the scientific climate in which he worked. During the late 19th and early 20th centuries, classical physics, based on the principles set out by Isaac Newton and James Clerk Maxwell, was considered the ultimate framework for understanding the physical world. Classical thermodynamics and Newtonian mechanics had proven incredibly successful in explaining macroscopic phenomena, from the motion of planets to the flow of heat. At this time, the universe was understood as a deterministic machine governed by precise laws that could predict future states if the current state was known. This was a worldview rooted in certainty and continuity, which was comforting to scientists of the era. However, at the microscopic level, there were growing concerns that classical physics could not fully explain certain phenomena. One of the most pressing problems of the time was the issue of black-body radiation. Black bodies are idealized objects that absorb all incoming radiation and emit radiation at a specific temperature. The problem was that classical physics, through the Rayleigh-Jeans law, predicted that the energy radiated by a black body would increase without bound as the wavelength of the radiation decreased. This led to what was known as the ultraviolet catastrophe, where theoretical models predicted an infinite amount of radiation at short wavelengths, which was clearly not observed in nature. It was in this context of uncertainty and a growing gap between theory and experiment that Planck entered the picture. Max Planck, while working on the problem of black-body radiation, found that classical physics could not explain the experimental results. As he sought a solution, he started questioning the foundations of energy exchange. Planck proposed that energy was not emitted or absorbed continuously, as classical theory suggested, but rather in discrete units, or quanta. This was a radical departure from classical thinking, where energy was considered to be continuous. In Planck's formulation, the energy of these quanta was directly proportional to the frequency of radiation, with Planck's constant h acting as the proportionality factor. The equation that emerged from this was equals sec E equals HNIU, where E is the energy, H is Planck's constant, and NIU nu is the frequency of radiation. This discovery was monumental, as it provided the first step toward the development of quantum mechanics. However, despite the mathematical elegance and empirical success of his solution, Planck was uncomfortable with the fundamental implications of his own work. Planck's reluctance to accept the broader significance of his quantum hypothesis is a fascinating aspect of his intellectual journey. Initially, Planck viewed the quantization of energy as a mathematical tool, something that was needed to solve the specific problem of black-body radiation, but not a new theory of the physical world. Classical physics had provided such a successful framework for understanding the macroscopic world that Planck had no desire to abandon it in favor of a new, probabilistic theory. The idea that energy could be quantized challenged the classical view that energy flowed continuously through systems. For Planck, the idea of quantization was a mere mathematical convenience rather than a fundamental feature of nature. His discomfort with this idea is evident in his early writings, where he downplayed the revolutionary aspects of his discovery and referred to the concept of quanta as a temporary solution rather than a deep insight into the fabric of the universe. While Planck may have been reluctant to accept the full implications of his work, his quantum hypothesis laid the foundation for future advancements. In the years that followed, other physicists, most notably Albert Einstein, built upon Planck's ideas. In 1905, Einstein used Planck's concept of quantized energy to explain the photoelectric effect, where light shining on a metal surface caused the emission of electrons. This demonstrated that light, traditionally thought of as a continuous wave, also behaved as if it were composed of particles, photons. Einstein's work further solidified the concept of quantization and helped to establish the dual nature of light, which could behave both as a wave and as a particle. This was a critical step in the development of quantum theory. Despite the groundbreaking nature of his work, Planck was not the first to embrace these new ideas. Albert Einstein, Niels Bohr, and Werner Heisenberg would all push the boundaries of Planck's theory, leading to the full development of quantum mechanics. However, Planck himself remained deeply rooted in the deterministic worldview of classical physics. He found it difficult to accept that the universe at its most fundamental level could be governed by probability and uncertainty, as the new quantum mechanics suggested. This philosophical divide between the classical and quantum worldviews became one of the central tensions in the early 20th century physics community. The transition from classical physics to quantum mechanics was not just a scientific revolution, but also a philosophical one. The deterministic laws that governed classical mechanics provided a sense of certainty and order, but quantum mechanics introduced a level of uncertainty that was deeply unsettling to many scientists, including Planck. Quantum mechanics suggested that at the microscopic level, particles did not have precise positions or velocities, and their behavior could only be described probabilistically. This was in stark contrast to the deterministic laws of classical physics, where the behavior of objects could be predicted with certainty. For Planck, and many others, this was a deeply uncomfortable concept. His work on black-body radiation had solved a pressing scientific problem, but it also hinted at a new way of understanding reality, one that was fundamentally probabilistic and uncertain. Even as quantum mechanics began to take shape, Planck remained cautious. In his later years, he did come to recognize the importance of quantum theory, but his acceptance of its broader implications was slow. He continued to wrestle with the philosophical implications of quantum mechanics, and it was not until the 1,920 seconds and 1,930 seconds, when the theory was fully developed by scientists such as Niels Bohr and Werner Heisenberg, that Planck began to embrace its full consequences. By this point, quantum theory had become the dominant framework for understanding the behavior of particles at the atomic and subatomic level. The probabilistic nature of quantum mechanics had been confirmed by numerous experiments, and it had led to new technological advancements, from the development of the transistor to advancements in atomic energy. Max Planck's journey from reluctant revolutionary to a key figure in the development of quantum mechanics is emblematic. of the challenges scientists face when confronted with new and revolutionary ideas. His work on blackbody radiation, though initially a mathematical solution to a specific problem, opened the door to an entirely new way of understanding the physical world. Even though Planck himself struggled to embrace the full implications of his discovery, his contributions remain foundational to modern physics. Planck's constant, h, remains one of the most important constants in physics, and his work continues to influence the field of quantum mechanics today. Planck's intellectual evolution mirrors the journey of science itself, one that is often fraught with uncertainty, struggle, and eventual transformation. Despite his initial reluctance, Planck's legacy as the father of quantum theory is secure. His work on the quantization of energy revolutionized our understanding of the universe at its most fundamental level. His contributions set the stage for the development of a new scientific paradigm, one that continues to shape our understanding of everything from the smallest particles to the largest cosmological structures. Through his work, Max Planck helped to open the door to a new era of physics, and his legacy remains one of the most significant in the history of science. Max Planck's work in the early 20th century marked the beginning of a scientific revolution that would completely alter the landscape of physics. His contributions were particularly vital in the formation of quantum mechanics, even though his own relationship with the theory was complex and, at times, uncomfortable. His discovery of quantized energy, derived from his work on blackbody radiation, solved a long-standing problem in physics and opened the door for the development of quantum theory. Yet, throughout his career, Planck's discomfort with the probabilistic nature of quantum mechanics reflected a broader tension between classical and quantum physics. Planck's journey began with his immersion in the classical physics framework, which had dominated the scientific world since the days of Isaac Newton. Classical mechanics, based on determinism and continuity, had successfully explained the macroscopic world. Energy was assumed to be a continuous quantity, and its interactions could be predicted with absolute certainty. This framework, which had been immensely successful in describing the behavior of objects at large scales, remained largely unchallenged as the best model for understanding physical phenomena. Planck, like many of his contemporaries, was raised within this framework and initially approached scientific problems with the assumptions of classical physics. However, the advent of new experimental challenges, particularly blackbody radiation, led Planck to question the sufficiency of these classical ideas. The problem of blackbody radiation had stumped scientists for years. Classical theories, particularly the Rayleigh-Jeans law, predicted that as the wavelength of radiation decreased, the emitted energy would increase without limit. This led to the ultraviolet catastrophe, a concept that contradicted experimental observations, which showed that the energy emitted by a black body did not increase infinitely at shorter wavelengths. The failure of classical physics to explain this phenomenon became a critical issue that needed resolution. Planck's solution to the blackbody radiation problem was nothing short of revolutionary. In his 1900 paper, Planck proposed that energy is not emitted or absorbed continuously, but in discrete packets, or quanta. This was a radical departure from classical physics, where energy had always been considered a continuous flow. Planck's hypothesis that energy could only be emitted in discrete amounts proportional to the frequency of radiation was a groundbreaking idea. His mathematical formulation, expressed in the equation E equals h/NIU, where E is the energy, h is the constant now named Planck's constant, and NIU is the frequency of the radiation, was the first clear indication that the laws of nature at microscopic scales were not continuous but quantized. This equation not only solved the blackbody radiation problem but also introduced the concept of the quantum, a notion that would lay the foundation for the entire field of quantum mechanics. However, Planck himself did not initially understand the full implications of this discovery. For him, the quantization of energy was a mathematical tool, a means of resolving the specific issue of blackbody radiation, rather than a profound shift in understanding the nature of the universe. Even as his work gained widespread recognition, Planck remained hesitant to fully accept the broader philosophical implications of his own discovery. At the heart of his reluctance was a deep commitment to classical physics. Planck had spent much of his career studying thermodynamics and the classical laws of energy, which were grounded in the belief that nature operated according to predictable, deterministic laws. The idea that energy could be divided into discrete packets seemed to violate this principle. Planck was not alone in his skepticism. Many of his contemporaries also struggled with the implications of quantum theory. Albert Einstein, while building on Planck's work, famously rejected the probabilistic nature of quantum mechanics, asserting that the universe was ultimately governed by deterministic laws. Even Niels Bohr, who developed the Bohr model of the atom, found it difficult to fully embrace the idea of a universe governed by uncertainty. In fact, Planck's intellectual struggle with the implications of quantum mechanics is a central theme in his work. He was a man who had been deeply influenced by classical ideas and found it difficult to abandon the deterministic worldview that had been so successful in explaining the macroscopic world. The quantum world, with its probabilistic and sometimes seemingly paradoxical nature, was something that Planck found difficult to fully embrace. His discomfort with the theory and his hesitance to accept it as the fundamental framework for understanding the universe reflect the broader intellectual and philosophical challenges that all scientific revolutions face. New theories are often met with resistance, not just from the scientific community, but from the intellectual traditions that have shaped the thinking of generations. Planck's reluctance to fully accept quantum mechanics did not diminish the impact of his contributions. His work provided the foundation for the development of the quantum theory, a theory that would soon explain phenomena that classical physics could not, such as the behavior of electrons in atoms and the wave-particle duality of light. Even though he was uncomfortable with the probabilistic nature of the quantum world, Planck's discovery of quantized energy changed the way scientists viewed the microscopic world. His work directly influenced future scientists like Werner Heisenberg, who would develop the uncertainty principle, and Erwin Schrödinger, who would further refine the wave theory of quantum mechanics. In the years following his initial discovery, Planck's ideas were expanded upon by other physicists, and quantum mechanics became the dominant theory in physics. Despite his initial reluctance, Planck ultimately accepted the importance of quantum theory. However, his intellectual journey, marked by skepticism and resistance, highlights the complex relationship between scientific discovery and personal belief systems. Planck's hesitancy to fully embrace quantum theory speaks to the challenges faced by those who push the boundaries of scientific understanding. Even as he changed the course of physics, Planck struggled with the very revolution he had helped to create. Max Planck's intellectual evolution provides an important lesson in the nature of scientific progress. His contributions to quantum theory, particularly his work on blackbody radiation, were instrumental in shaping the future of physics. Yet, his reluctance to accept the full implications of his work also serves as a reminder that scientific revolutions are often accompanied by uncertainty and resistance. Planck's journey from reluctant revolutionary to a key figure in the development of quantum mechanics demonstrates the complexity of scientific discovery and the personal struggles that often accompany it. While Planck did not fully embrace quantum mechanics during his lifetime, his work continues to be one of the most important milestones in the history of science, and his legacy remains central to the understanding of the quantum world. Max Planck's contributions to the development of quantum mechanics were transformative and have left an indelible mark on the landscape of modern physics. One of the central aspects of his work was his formulation of quantum theory, which arose from his efforts to solve the black-body radiation problem at the turn of the 20th century. This issue had been a major challenge for classical physics, and Planck's approach introduced the revolutionary idea that energy is not emitted continuously, but in discrete packets, later known as quanta. The discovery laid the groundwork for what would become quantum mechanics, though Planck himself remained cautious about fully embracing the revolutionary nature of his own work. Despite his reservations, Planck's contributions were foundational, influencing not only his contemporaries but the entire course of 20th century physics. The problem of black-body radiation was one of the key challenges facing physicists in the late 19th century. Classical physics, particularly the Rayleigh-Jeans law, predicted that the radiation emitted by a black body would increase without bound as the wavelength of the radiation decreased. This theoretical result led to the so-called ultraviolet catastrophe, where classical physics could not account for experimental observations. The predictions of the classical theory were at odds with experimental data, particularly at shorter wavelengths, where the energy emitted by a black body appeared to be finite, not infinite as classical physics suggested. This discrepancy led to confusion and frustration among physicists who could not explain the observed behavior of radiation. Max Planck's breakthrough came when he introduced the idea that energy is quantized. To solve the black body radiation problem, Planck proposed that the energy exchanged by matter could only exist in discrete amounts, or quanta, rather than in a continuous flow. This idea was radical and represented a departure from the classical view that energy could be divided infinitely. Planck's mathematical formulation, which related the energy of the quanta to the frequency of the radiation, led to the equation E equals hNIU, where E is the energy, h is Planck's constant, and NIU is the frequency. This equation not only resolved the black body radiation problem but also laid the foundation for the development of quantum mechanics. However, Planck himself did not initially recognize the full significance of his discovery. He considered the quantization of energy as a mathematical convenience to resolve a specific issue rather than as a fundamental change in our understanding of the laws of nature. Despite the importance of his work, Planck was deeply reluctant to accept the broader implications of his own discovery. Classical physics had been immensely successful in explaining the macroscopic world, and Planck, like many physicists of his time, was reluctant to abandon the deterministic worldview that had dominated science for centuries. His discomfort with the idea of quantized energy arose from the probabilistic nature of the new theory. Classical mechanics had been deterministic, meaning that if the current state of a system was known, its future could be predicted with certainty. Quantum mechanics, on the other hand, introduced an element of uncertainty and probability, particularly in the behavior of subatomic particles. This shift was uncomfortable for Planck, who had spent much of his career within the framework of deterministic physics. Planck's intellectual struggles were not unique. Many of his contemporaries, including Albert Einstein, shared his discomfort with the probabilistic nature of quantum mechanics. Einstein, for example, famously expressed his skepticism of quantum theory by saying, "God does not play dice with the universe," reflecting his belief that the universe must be governed by deterministic laws. In a similar vein, Planck remained hesitant to fully embrace the probabilistic nature of quantum mechanics, even as other physicists, such as Niels Bohr and Werner Heisenberg, developed and refined the theory. Planck's reluctance to accept the full implications of quantum mechanics is a reflection of the broader philosophical challenges that scientific revolutions often provoke. New ideas, especially those that challenge deeply held beliefs, are often met with resistance, even by those who have contributed to their development. Despite his initial reservations, Planck's work laid the foundation for the development of quantum theory. His idea of quantized energy was central to later developments in quantum mechanics, including the work of Heisenberg, Schrödinger, and Bohr. For example, Heisenberg's uncertainty principle, which asserts that the position and momentum of a particle cannot both be precisely determined at the same time, is deeply rooted in the probabilistic nature of quantum mechanics. Similarly, Bohr's model of the atom, which introduced the concept of quantized energy levels, was directly influenced by Planck's work. Although Planck struggled with the implications of his own theory, his contributions became a key piece of the puzzle that eventually led to the development of a full quantum mechanical framework. In recognition of his contributions, Planck was awarded the Nobel Prize in Physics in 1918. This accolade was not only a recognition of his work on black-body radiation but also acknowledged his role in the birth of quantum theory. Planck's role in the development of quantum mechanics was central, even though he did not live to see the full realization of the theory he had helped to shape. By the 1920 seconds and 1930 seconds, quantum mechanics had become the dominant framework for understanding the microscopic world, and its applications were being explored in fields ranging from atomic physics to solid-state physics. However, Planck's cautious approach to the theory reflects the intellectual journey that many physicists had to undertake as they shifted from classical to quantum thinking. The tension between these two frameworks, classical physics and quantum mechanics, was not just a scientific transition, but also a philosophical one, as it forced scientists to reconsider the fundamental nature of reality itself. Max Planck's contributions to physics were revolutionary, and his legacy as the father of quantum theory is secure. His work laid the groundwork for an entirely new way of understanding the physical universe. However, Planck's journey was not without personal conflict, as he struggled to reconcile the implications of his work with his long-standing attachment to classical physics. His discovery of quantized energy, though initially viewed as a mathematical tool, ultimately transformed our understanding of the microscopic world. Planck's contributions remain foundational in modern physics, and his intellectual journey is a reminder of the challenges that come with scientific progress, especially when it challenges deeply held beliefs about the nature of reality. Through his work, Max Planck helped to usher in the quantum age, a new era in physics that continues to shape our Planck understanding of the universe today. Max Planck's pivotal role in the development of quantum theory is rooted in his work on black-body radiation, which became one of the most important scientific problems of the late 19th century. Classical physics, with its well-established framework for understanding macroscopic phenomena, was facing challenges when it came to explaining the behavior of light and heat at microscopic levels. The laws governing thermal radiation, in particular, were at odds with experimental data, and the inability to resolve these discrepancies marked a critical turning point in the history of physics. It was in this context that Planck's work led to one of the most groundbreaking discoveries of the 20th century, the idea that energy is quantized. The black-body radiation problem arose because classical physics predicted an unbounded increase in energy as the wavelength of radiation shortened, a phenomenon known as the ultraviolet catastrophe. This was in stark contrast to experimental results, which showed that the radiation emitted by a black body decreased at short wavelengths. Physicists had no explanation for why classical predictions failed to match reality. Planck, who had already established a reputation for his work in thermodynamics, was tasked with solving this puzzle. His approach was revolutionary, as he introduced the concept that energy could be emitted or absorbed only in discrete quantities, or quanta, rather than continuously. Planck's hypothesis that energy is quantized in proportion to frequency would serve as the foundation for the development of quantum theory. Planck's equation, E equals hNIU, where E is energy, h is Planck's constant, and NIU, nu, is frequency, provided a solution to the blackbody radiation problem and introduced the world to the quantum. This mathematical relationship was not only instrumental in solving the immediate problem, but also opened the door to a new way of thinking about energy and the fundamental nature of matter. The constant h, now known as Planck's constant, would become one of the most significant constants in physics, deeply influencing later developments in quantum mechanics. However, despite the success of his theory in explaining radiation, Planck himself was reluctant to embrace the full philosophical implications of his work. He viewed his quantum hypothesis as a mathematical tool, a temporary fix rather than a fundamental rethinking of nature. Despite the profound implications of his discovery, Planck struggled to fully accept the nature of the quantum world he had uncovered. Classical physics had provided scientists with a deterministic view of the universe, where the future of any physical system could be predicted if its current state was known. Planck's own attachment to this deterministic worldview made it difficult for him to accept that nature at its most fundamental level might not be entirely predictable. Quantum theory, with its reliance on probabilities and uncertainties, posed a challenge to the deep-seated beliefs of physicists like Planck. He initially saw his work as a mathematical expedient, a means to solve a specific problem rather than as a fundamental shift in the way the universe functioned. This reluctance to embrace the probabilistic nature of quantum mechanics was shared by other physicists of his time, including Albert Einstein, who also struggled with the philosophical implications of the new theory. While Planck himself remained cautious about the full implications of his work, the consequences of his discovery were quickly realized by others. Albert Einstein, in 1905, applied Planck's quantum hypothesis to explain the photoelectric effect, where light shining on a metal surface causes the emission of electrons. This application of Planck's work provided further evidence for the validity of quantization and established the concept of the photon, a quantum of light. Einstein's work demonstrated that light had both wave-like and particle-like properties, a duality that would become central to quantum theory. In this way, Planck's ideas laid the foundation for some of the most profound breakthroughs in physics, even though he was not fully prepared to accept the implications of his own discoveries. As quantum theory developed through the work of Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, Planck continued to grapple with the nature of quantum mechanics. While others embraced the full potential of quantum theory, Planck remained hesitant about abandoning the classical worldview. This intellectual struggle, however, was part of a broader theme in the history of science: the tension between old and new paradigms. Scientific revolutions are rarely straightforward. They are often met with resistance, especially from those who have made significant contributions to the old paradigms. For Planck, the acceptance of quantum mechanics was a slow and difficult process, marked by his deep commitment to the ideas that had defined his career. Max Planck's reluctant embrace of quantum mechanics was not a rejection of the theory itself, but a reflection of the intellectual and philosophical challenges that arise when established scientific ideas are overturned. His work, particularly on blackbody radiation, marked the beginning of the quantum era, and while he may have struggled with the deeper implications of his own discoveries, his contributions were foundational to the field. Planck's introduction of quantized energy was the first step in a series of developments that would change the course of physics. His reluctance to fully accept the probabilistic nature of the quantum world speaks to the intellectual discomfort that often accompanies groundbreaking scientific progress. Even in his later years, when the foundations of quantum mechanics were fully established, Planck continued to serve as an intellectual bridge between the classical and quantum worlds. His legacy as the father of quantum theory is secure, and his work remains central to modern physics. The Planck constant, which he introduced to solve the black-body radiation problem, remains one of the most important constants in science. His intellectual journey, marked by reluctance and resistance, is a testament to the complexities of scientific discovery. Planck's legacy, as a key figure in the birth of quantum mechanics, serves as a reminder that revolutionary ideas often require not just intellectual brilliance, but also a willingness to confront deeply held beliefs and embrace new paradigms. Through his contributions, Max Planck helped to open the door to the quantum age, forever changing our understanding of the universe. Max Planck's journey into the world of quantum mechanics was one of intellectual discovery, but also one of deep personal conflict. Born in 1858 inches, Kiel, Germany, Planck was raised in an academic environment that valued scientific inquiry and rigor. His initial education was grounded in classical physics, which adhered to deterministic laws of nature. Classical physics, influenced heavily by the works of Newton and Maxwell, was based on the idea that the universe operated according to predictable, continuous rules. Energy, for example, was thought to flow continuously through systems, and the universe could, in theory, be understood through these fixed laws. However, as Planck entered his professional career, the limitations of classical physics began to surface, particularly in the area of thermodynamics and the study of radiation. The problem of black-body radiation, which arose in the late 19th century, was one of the most pressing issues in physics. Classical theories, especially the Rayleigh-Jeans law, predicted that energy emitted by a black body would increase without limit as the wavelength of the radiation shortened. This led to the ultraviolet catastrophe, a discrepancy between theoretical predictions and experimental data. Physicists, unable to resolve this contradiction, were left searching for an answer. It was in the context of this challenge that Max Planck began to formulate the theory that would eventually lay the foundation for quantum mechanics. Planck's breakthrough came when he introduced the idea that energy could be emitted or absorbed in discrete units, or quanta, rather than as a continuous flow. This concept was a radical departure from the classical understanding of energy. His quantum hypothesis posited that the energy of radiation was proportional to its frequency, with the proportionality constant being a new quantity, Planck's constant, h. The equation that emerged, E equals h NIU, where E is energy, h is Planck's constant, and NIU is the frequency of radiation, provided a solution to the black-body radiation problem and set the stage for the development of quantum theory. However, despite the elegance and success of his mathematical formulation, Planck himself was initially reluctant to accept the full implications of his discovery. His introduction of the quantization of energy was not intended to challenge the laws of classical physics, but to provide a temporary mathematical fix for a specific problem. Planck was deeply rooted in the deterministic worldview of classical physics, and he viewed his quantum hypothesis as a tool to resolve a particular issue in radiation theory, rather than a fundamental shift in the understanding of the physical universe. This reluctance was further complicated by his attachment to the ideas of continuity and predictability that had governed scientific thinking for centuries. In the years following Planck's discovery, his quantum hypothesis gained recognition, but it also sparked intense intellectual debate. The work of other physicists, particularly Albert Einstein, who applied Planck's idea to explain the photoelectric effect, demonstrated that the quantum nature of energy had far-reaching implications beyond black-body radiation. Einstein's work on the photoelectric effect in 1905 not only confirmed Planck's theory but also introduced the idea of light quanta, or photons, showing that light exhibited both wave-like and particle-like properties. This wave-particle duality became a central feature of quantum mechanics and led to the development of quantum theory in its entirety. Despite these advances, Planck continued to struggle with the philosophical and conceptual shifts introduced by quantum mechanics. Classical physics had provided a deterministic framework that many scientists, including Planck, were unwilling to abandon. The probabilistic nature of quantum theory, where the outcomes of physical events could only be predicted in terms of likelihood rather than certainty, was a deeply unsettling concept. For Planck, the idea that the universe could be fundamentally governed by uncertainty was difficult to accept. He was not alone in this struggle. Einstein also famously expressed his discomfort with the probabilistic interpretation of quantum mechanics, famously stating, "God does not play dice with the universe." Despite his intellectual hesitance, Planck's work became the foundation for the broader development of quantum theory. The probabilistic and uncertain nature of quantum mechanics was further developed by Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, who built on Planck's ideas to explain atomic structure, wave functions, and the uncertainty principle. The birth of quantum mechanics not only revolutionized the understanding of the microscopic world, but also had profound implications for the nature of reality itself. Quantum theory challenged long-standing assumptions about determinism and predictability, suggesting that at the fundamental level, nature operates according to probabilities and wave functions. Even though Planck did not fully embrace the philosophical implications of his work, his legacy as the father of quantum theory is firmly established. His work on blackbody radiation and the introduction of quantized energy paved the way for the development of quantum mechanics. Planck's constant h became a cornerstone of quantum theory, and his contributions were recognized with the Nobel Prize in Physics in 1918. However, Planck's personal struggle with the implications of his discovery reflects the broader intellectual tension that often accompanies groundbreaking scientific revolutions. Scientific progress is not just about uncovering new facts, but about changing the way we perceive and interpret the world. For Planck, this intellectual transformation was both a source of personal conflict and a cornerstone of his contributions to science. In later years, Planck came to accept the significance of quantum theory, but he never fully embraced the philosophical upheaval it caused. He continued to hold on to the idea that the universe had an underlying determinism, even as quantum mechanics suggested a fundamentally probabilistic reality. Nonetheless, his work provided the foundation for a new understanding of the universe, one that has since become the cornerstone of modern physics. The advent of quantum mechanics has led to groundbreaking advancements in technology, from the development of semiconductors and lasers to the creation of quantum computers, and continues to shape scientific inquiry in the 21st century. Max Planck's contributions were pivotal in the development of quantum mechanics, and his discovery of quantized energy remains one of the most important milestones in the history of science. While Planck was reluctant to fully accept the revolutionary nature of his work, his ideas reshaped the field of physics and opened the door to a new era of scientific discovery. His intellectual journey, from classical to quantum physics, is a testament to the complexities and challenges that accompany scientific progress and the acceptance of new, paradigm-shifting ideas. Planck's legacy, however, is secure as the father of quantum theory, and his work continues to inspire and guide the scientific community today.